Yes. So welcome again to this channel. Today we are looking at Boas optimization models. Just a little more, just a bit. Yes. So we are seeing here Boas optimization models. We have cylindrical model, we have a cuboid model, we have a conical model, and we have pyramidal models. You might be asking yourself, what are these models? So these are my findings, my models that I've come up with after doing some little research and doing some little geometry and algebra, playing with the formulas of these 3D objects like the cylinder, the cuboid, the conical, the cone, and the pyramid. And I've come up with the formulas or models that can be used in that can be used for economical purposes. And we are going to see how these models are going to work and how I've derived these models, and they are new, and I'm really waiting for the day I'll be called and present these formulas or these models to the world so that they may be known. And as Africans, you will have to be very happy with this. You have to be very happy with this. These are the findings from the Africa, and we need to be very happy. So if you are any African or a mathematician watching this, you have to subscribe for support, to support me and to push this video so that these models can be published, and we can be, so that to be proud of our Africa, because we are also potentials. So let me begin today with the cylindrical model. So what is cylindrical model? Cylindrical model, let's begin with the closed, and there's a closed and for an open system. So today we are going to begin with the Boas closed cylindrical model. So we have derivation and the optimization and the applications part. So how did I derive these formulas? So let's have the introduction. This presentation explores Boas closed cylindrical model, derived from geometric principles and optimized for practical design. It connects surface area, volume, and the radius of the closed cylinder. So here we have a closed system of a cylinder. Let radius be the r, height be the h, and a is the surface area of the cylinder, of course the closed system, and the volume. Then we have surface area as A is equals to 2 pi r squared plus 2 pi r h, and volume is pi r squared h. As we know, those are the formula of the surface area and the volume of a closed system of a cylinder. So let's go down to derivation of Boas closed cylindrical model. From the expression of the volume is V is equals to pi r squared h. Making h the subject formula, we are going to have h is equals to V over pi r squared. Then substitute that expression into the expression of the surface area, which is 2 pi r squared plus 2 pi r h. So having h is equals to V over pi r squared, we are going to insert the way it has been inserted there, and of course you multiply both sides, the a part and the expression, both side by r, and doing your simplification you are going to remain with ar on the right side is equals to 2 pi r cube plus 2v, where v is the volume and a is the area. Then rearranging to set this formula into to 0, we are going to have 2 pi r cube minus ar plus 2v is equals to 0. This is the Boas model, and this model we are going to see how it's really helping and how it is applicable in the real world problem or real world application and designs for even the economical purposes. So let's go ahead. So the optimization model the economic model now, economical model of this formula. We are going to differentiate that expression, the 2 pi r cube minus ar plus 2v. I've said a there is for the area and v is for the volume. So differentiating with respect to r, we are going to have 6 pi r squared minus a. Then we set that one to 0, because for most economical model we are going to find the derivative of the function, then we set it to 0, so that we have either the maximum or the minimum model of this kind of equation. So for this case, that one is called the economical model. So having doing that, we are going to have a is equals to 6 pi r squared. So that one means for any economical model of a cylindrical system, which is a closed system, the area is equals to 6 pi r squared, and then the volume from the optimization, the volume is equals to 2 pi r cube. That is the volume. Why is v, the volume, is equals to 2 pi r cube? Down here you can see v is equals to pi r squared h, and also 2 pi r cube is an expression of v for most economical. Doing the simplification, we are going to have h is equals to 2r. h is equals to 2r. Now if you substitute that one back to the expression of the volume, you are going to have 2 pi r cube is equals to v. So for most economical system of cylindrical cylinder which is closed, we have surface area as 6 is equals to pi r squared, and the optimized volume is equals to 2 pi r cube. Let's look at the summary now. The model is closed system. The surface area of the most economical system is 6 pi r squared. Volume is 2 pi r cube. Note that. So application, we can apply this model in water tanks and silos, pressure vessels, chemical reactors, seal storage containers. These are some of the real world applications where this model can be used. And let's look at practical application for this model, which is very new. It's brand new. It's a 2025 findings. It's a 2025 findings derived model that can be helpful in designing most economical cylindrical systems. So question number 1 on practical application, we have an NGO is planning to construct a concrete cylindrical tank that can hold a capacity of V meters cube of water to serve the villagers, full stop. They expect the tank to be 14 meters wide and that it must be most economical. You are presented with this contract to estimate the capacity that the tank can hold in liters. Assume the closed system. Use Boas optimization model for cylinders to determine the volume V and the surface area given as A. Now to the solution part. For closed system, the model is 2 pi r cube minus ar plus 2v is equals to 0. This is the model that we are going to use. And remember, for the most economical system, A is 6 pi r squared, and having that, we are simply going to substitute r as 7. Why is r 7? Remember, we are told that the cylinder is going to be 14 meters wide, so that is the diameter. This means area, the radius is 7 meters. Now we are going to substitute r into this expression of A because it is most economical system, and the area for most economical system of a closed cylinder is 6 pi r squared as derived. So inserting r, we are going to have the expression of A as 923.748 meters squared. So this is the expression of R, or this is the surface area of this most economical system of a cylinder. Then we want to go ahead and find h, so that we may be able to find the volume. Remember we said h is equals to 2r. Remember we said the h is equals to 2r. H is equals to 2r. Now let us use this expression first, where h is equals to a minus 2 pi r squared, everything over 2 pi r. As you can see, this expression is derived from the expression of the surface area, the total surface area of a closed system of a cylinder. If you make h the subject formula from that expression, we are going to have a is equals to 2 pi r squared over 2 pi r. Now substituting a into this expression, we are going to have, as you can see, we are going to have there 923.748 minus 2 into pi times 7, which is the r squared, then over 2 times pi r. So having that, simplifying and calculating, you are going to have h is equals to 14 meters. Now from the economical elements, we had h is equals to 2r, and remember area is 7, so h automatically is going to be 14 meters. So even without going through this process that we have done, you can simply go and use h is equals to 2r, so that you have h is equals to 2 times 7, which is 14 meters. Now we can go ahead and find the volume or the capacity of this model. So we have pi times r squared times h. We have the h, we have the radius, so we simply insert what we have, then we do the volume, which gives 2155.412 meters cube. And remember, the question said that we find the capacity in liters, so 1 meters cube is equals to 1,000 liters. Inserting that, we are going to have a capacity of 2,155,412 liters. This is one of the application of this model, and you can see how it works really well. It works really well. Imagine you are only given one dimension, you are only given the radius or a height or the diameter, and you are expected to compute the volume, compute the surface area. Using Bohr's model, it is very simple, and you can use that model to compute such a problem. And for most economical systems, it also works best. And of course, you can see for most economical system, h is equals to 2r. That means h is twice the radius. For any cylinder that is considered optimal or economical, h must be twice the radius. Let's go ahead and look at the second practical application. It says Kitmiki Mineral Water is planning to construct a water tank that can hold a maximum capacity of 2,771,244 liters, covering a total surface area of 1099.7 meters squared. Assume a closed system. Use Bohr's optimization model of a cylinder. 2 Roman 1. Show that the height of the tank is given by h is equals to 175 minus pi r squared over r. Roman 2. Find the radius of the tank and the height that is optimal. Then Roman 3. Verify if the results are optimal. Before we do this question, I wanted to note that for this case, we are given the volume and we are given the surface area. So we have to look for the radius and the height, and then we confirm if those values are optimal. So one of the application of Bohr's model, it helps you to compute the dimensions of any 3D object when you are provided with only area and the volume. You can easily compute the dimension of any 3D object given the volume and the surface area using Bohr's models. It is very simple. So in this case, we are not told that this model was or this cylinder was most economical, so we are not going to apply the economical elements model in this case. So in this case we are just going to use Boas model to find the radius and to find the h, I mean the dimensions of this kind of cylindrical tank that the Kitmikai Mineral Ltd water wanted to construct. Now let's go ahead and do Roman 1. So they have told us to show that h is equals to 175 minus r squared over r. How about that? We know that h is equals to a minus 2 pi r squared over 2 pi r, as we said earlier, and the closed system model is 2 pi r cubed minus a r plus 2v is equals to 0. So a we are given, which is the surface area, as 1099.7. Substituting that, we are going to have 1099.7 minus 6.284 over 2.84 r squared over 2 pi r. Then we are going to factor out 6.286. What is 6.286? 6.286 is simply 2 pi. 2 pi. In this case, we are using pi as 3.142. So 2 pi is 6.284. So factoring out that from the expression of h, we are going to have 6.284 in bracket 175 minus r squared over 6.284 r. Remember, in the denominator we only have 2 pi r. We have 2 pi r and we are only factoring out 2 pi. So we are going to remain with r in the denominator. Then simplifying this, we are going to remain with the h is equals to 175 minus r squared over r. And that is done. Then Roman 2, the question says that we compute for the radius and their height. Now this is where a student need to be very keen when applying Boas optimization model, and it is not hard, it is very simple. We are going to recall that the volume we are given into liters, and here we are dealing with meters. So we convert it first into meters, and then we are going to have A as 1099.7 as given, and V, the volume, is going to have 2771.244 meters cube. So substituting them into the model, 2 pi r cube minus ar plus 2v is equals to 0. We are going to have that F is equals to 6.284 r cube minus 1099.7 r plus 2v, which is 5542.488 is equals to 0. Now you have this function. What next? As you can see, note that the function above is a depressed cubic function. A depressed cubic function means it has a cubic element and it doesn't have any squared element. Instead, it has only to the 1 degree and the 3rd degree. So this kind of function is called a depressed function, which requires various special methods to solve so that you find the real roots of this function. So in this case, we are going to apply the numerical method. A numerical method here is it entails kind of trial and error, but it's very simple and it's very accurate. Now look at this. We are going to assume r is equals to 1 or 2 or 3 or 4 or 5 or 6 or 7 or any other, so long as it satisfies the function. So r cannot be 0. Why? Because logically a dimension of an object can never be 0, and dimension of an object can never be 0. So logically r must be greater than 0. That's why I've begun from r is equals to 1. So when r is equals to 1, the function is going to be 4449.07 all the way to 6, then 7. So at r is equals to 7, the function is satisfied. We are getting 0. So that means from the above method, the function is satisfied only when r is equals to 7. And if you do this in a graph, you are going to do that. You might end up having other values, but these values are going to be negative. So Obviously we will ignore, because logically again a dimension of an object can never be a negative, it can never be 0. Remember we said r is greater than 0, therefore h, they said h is equals to 175 minus r squared over r, and then we have r as 7. So substituting this r, which is 7, into the formula, we are going to have h as 18 meters. So we have radius 7 and height 18 meters. And in case the radius is decimal, because we do not know whether when we are using numerical method, we do not know whether the radius is going to have a decimal point. So the best thing to know this is by going ahead and plotting the values that you have in a graph, so that perhaps the radius was a decimal. Graph will definitely indicate that the optimal radius is that. So since the function f is satisfied when r is equals to 7 as the above, then we have to say that the function is satisfied, because if you substitute into the model, which is 2 pi r cubed minus ar plus 2v is equals to 0, if you substitute r as 7 and a as 1099.7 and v as 2771.244 into that model, you are going to have 0. So that means Roman 3 is also answered, which said verify if the results are optimal. Now into the graph. This is the graph. As you can see, when r is 0, when the function is 0, y is 0, when r is 7 here, when x is 7 I mean. So at this point my function was y is equals to 6.284 x cubed minus 1099.7 x plus 5. So here I've used x, then I've used y instead of f and x instead of r, which is also just the same. So plotting this in the graph, this is just a portion of the graph. So we have here, as you can see, it is satisfied at 0 when x is 7. So this graphical method can really be helpful, especially when r is not known if it is decimal or non-decimal r. So graphical method gives us the radius that are decimal, that are in decimal points. So that is that. So conclusion of this model, as you can see, it's very simple to use and it's very much easy to understand. This closed system model provides an analytical structure for efficient cylindrical designs. The economical model highlights the optimal balance between material usage and storage capacity. So those are the practical application of this model. So what do you say about these models? Because as you can see, the cylindrical model for the closed system is that, and it's very nice, and it's a very new model that is recently derived. Of course I derived it this year 2025. So to all Africans, to all Kenyans especially, you have to be very proud of your of this guy. You have to be very proud of this guy, because this is a Kenyan model and it's very new. I'm just waiting for me to be called and present this model to the world. There are so many more to do with the cuboid model, conical model, pyramidal model, and both of them has the open and the closed system. So there are still much more that I have to share, so that it may be known, that may be published, so that the engineers can use these models, and the companies can use the economical models to make much more profit, and many more that can be done with this model. So tune in to the next video where I'm going to do the open system for the cylinder, and then I'll also do for the rest of the models, and we shall see how they can be applied into the real world problems. So share this video again, and you can subscribe, and you can also like the video, and be proud, Africans, be proud once again for these models, because they are going to put us somewhere as Africans. At least a model is going to be named after an African guy called Boaz Otieno, which is me sharing with you these insights of mathematics. Just simple geometry and simple algebra, we can form so many things, and a lot can be done for the best of the economy, and for the best of our continent, and for the best of the world entirely. So thank you for watching. Tune in for the next video, where we are going to share about the open cylindrical model. Thank you for watching, and have a nice time.